1986 question. Again, it's dealing with stoichiometry and some other stuff here. Three volatile compounds, X, Y, and Z. Now, before we go any further, make sure you know what the term volatile means, or volatile, however you want to pronounce that. Volatile means that it simply evaporates easily at room temperature. Now, we're conditioned based on what we've done so far, what we've experienced in life, that most volatile substances are also flammable. That is true for a lot of examples, but what we want to know about this is that volatile simply means that it evaporates easily at room temperature. Also, we have three compounds, so that's not an element or a mystery element. So we have three compounds, X, Y, and Z. And it says each of these compounds contain element Q, which we don't know what it is. The percent by weight of element Q in each of these compounds, or in each of the compound, was determined, and here's our data. Some of the data obtained are given below, so what wasn't given is the molecular weight of whatever compound X is. So that probably means that we're going to have to find out what that is. So let's go ahead and answer the questions. And again, this is all information, important information. Actually, this table, for the most part, is very important information. So that's really what we want to focus on. We just know that Q is making up these compounds, whatever these compounds are. So let's look at the first one, A. It says the vapor density, actually let me do this. Let me erase that. There, we don't need that in there. All right, so A says the vapor density of compound X at 27 degrees, 750 millimeters of mercury was determined to be 3.53 grams per liter. Calculate the molecular weight of compound X. True. This type of question was not asked in the summer packet. However, it was something that we discussed in pre-AP chemistry or honors chemistry. So again, we're looking for the molecular weight or molar mass. So retrieve your memories back to not too long ago, and you get to use PV equals nRT. All right. Now, you do have this equation on your equation sheet, which is nice. But you also have another equation that's on your equation sheet that looks like this. That PV equals nRT, and also that N can represent little m over big M. Now remember that little m, in this case, represents the mass of your compound, or your thing, whatever it is that you're looking at. And big M represents the molecular mass, or the molar mass, however you want to say that. So what we're going to do is we're going to need to substitute this into this equation and solve for big M. And I think we have everything that we can do that. So that's what part A is, so let's do that. So I'm going to substitute that, so PV, little m over big M, RT. So that's how our equation looks. Now we want to isolate variables, so that means that I will multiply the molar mass on both sides, and I will divide P and V on both sides. So now my equation looks like this. So if I were to rewrite it, I'd have big M equals little m RT over PV. Now, there's some information that was given to us that may cause me, or that I may want to rearrange. Let's look at what's given. I'm given a temperature. Beautiful. I'm given a pressure. Beautiful. I'm given 3.53 grams per liter. So I may want to rearrange, and if you're not sure what that is, that's actually a density. So the better way to rearrange this equation would be to do this. Is that big M is equal to M over V times RT divided by P. Okay? That's probably the best way to rearrange your variables. And I highly recommend that you rearrange your variables before you plug any values in. It just will keep you out of trouble. It'll save you a lot of heartache. I'm just telling you, it's the best thing to do, and AP graders love it when you show this. If you have me in class, I insist that you show it this way. Okay? So let's go ahead and plug in our numbers here. So let's see. We know our density that was just given at 3.53 grams per liter. So 3.53 grams per liter. So that takes care of my mass and my volume. So I'm good there. And let's see, my R, let's see, we're working with millimeters of mercury. On your equation sheet, you do have the conversion that does this. That 1 atmosphere is equal to 760 millimeters of mercury. I would use that. I would use that. So in this case here, we know that we have 750 millimeters of mercury. Also, we have an R value that has millimeters of mercury. So I don't care which way you do it. I actually prefer to use the 0.0821 as my R value. So I'm actually going to do a sidebar equation. And you don't have to do this. There is an R value on the equation sheet. And let me go get it. So our R value, and there is a value on your equation sheet, and you probably have never used this before, but it's okay. We are used to the R value that is 0.0821, and that's atmosphere liter per mole Kelvin. You're also familiar with the 8.315 that is the kilopascals, but we don't use kilopascals in AP chemistry, so we're not going to use that one. So we could use this one, but we also could use the one that's listed near the bottom where it says gas constant R, which is this value here. That, and again, it's pretty cool. It's a 62, and I don't use it very often, but if I don't have to make a conversion, I won't. So 62.36 liters, and that's, again, we're going to keep all the units. We're going to show all of our units when working this out. So 62.36, and that's liters on the sheet. Torr, now, you're probably going, whoa, torr, it's in millimeters of mercury. Remember that 1 millimeter of mercury is equal to 1 torr pressure. Okay? So that is acceptable. So we can use this number here, and we can say, if you don't like that torr, you can get rid of that. And if you want to say that's in millimeters of mercury, you know what? I can live with that. That's fine. But also be sure to put the other units in. So we have our mole Kelvin on the bottom. I think what the other ones were. So I'm going to put that down there. And then again, this is all part of my R value. But if you're not comfortable with that and you want to take your 750 milliliters divided by the 760 to get your atmosphere, that's fine. That is okay by me. Let's get rid of you. You don't want to be over here, Tor. And let's see, we have our 27 degrees as our temperature. So 27 plus 273, and that'll be given to you. So in that case, it's 300, right? Yeah, that's 300 Kelvin. So 300 Kelvin. And the pressure was 750 millimeters of mercury. Okay, so let's cancel out the terms that we can. Kelvin are gone, millimeters of mercury are gone, liters are gone. What units, plural, what units remain? Very good, we have grams per mole, which is what we want to see because we're looking for molar mass. So let's get a number here. 88. We'll say 0.5. And if we were doing sig figs, how many sig figs should we have in our answer here? I see 2, I see 3, I see 3. I'm going to stay with 3. I see a lot of 3s here, a lot of 3s there. I think that 27 isn't very good. So I'm going to go with 3 sig figs. So the best answer that I can show here is 88.1 grams. If you wrote 88, that's fine. All right. Part B. Now again, this part right here was not in the summer work, but you may see something like this on the test. And you're still responsible for all the material that you learned last year. So it's not a process where we forget things and then we restart over again. Okay, keep that in mind. This is a college type course. All right, part B. It says determine the mass of element Q contained in 1 mole of each of the 3 compounds. Okay, so we found up here, we found the molar mass, which is 88.1. Well, the units are up there. It's molar weight, grams per mole. Okay, so we have that value now. All right. So element Q, so let's determine the mass of element Q in each of these 3 compounds. So we're going to change that to a fraction or a decimal and multiply it by that. So let's do that. This is rather easy. And let's get some numbers. All right. And I got 57.1. And this one was 75.9, and this one was 37 point, I'll say 38. My calculator says 37.952. Okay, so there is part B, the most probable value of the atomic weight of element Q. Calculate the most probable value of atomic weight of element Q. All right, so what this question is asking, part C, is asking us to find like a commonality here in which all of these can go into a common element's mass. What we need to do is find the most common denominator of these values. Some denominators. Let's do this. So 57. And again, I'm writing denominators for these down. 70, we'll say 76. Yeah, 38. Okay. Now this, I would be very surprised if this is a question that's ever asked again on the AP exam, but interesting. So 1 and 57 obviously are denominators. Can 57 go 3 times? $57, 3, 19, 57. Can, I think that's looking good. 57, can that be divided by, obviously not by 7. No. All right, so 1, 3, 19, and 57. Ooh, 38 can be 1, 2, 19, 38. Can 38 go? Well, we have 2 denominators of 19. Can 76 go into 19? 4 times. Hey! So 4 times 19 is equal to that. So our common denominator, and this is, in my opinion, that's a crazy question to be asking. So 19. So you math geeks out there, I guess, could do that. Or maybe when if you're in my class, you'll be using the TI Inspire. Maybe there'll be a program that we can write, or maybe you'll have a program where you can find common denominators. Oh boy, that was fun. So the most probable mass for element Q is 19. Compound Z contains carbon, hydrogen, and element Q. When 1 gram of compound Z is oxidized and all of the carbon and hydrogen are converted to oxides, 1.37 grams of carbon dioxide and 0.281 grams of water are produced. Determine the most probable molecular formula of compound Z. All right, so here's what I'm going to do. I'm going to write down what they have given us. So we have a compound. Compound Z contains carbon, hydrogen, and element Q. So we have carbon, hydrogen, and whatever Q is. Okay. And we're going to find what that is. Okay. The question says that it reacted with oxygen, or it was the carbon and the hydrogen were oxidized. Actually, let's get this all down. So it reacted with oxygen, and we don't know how much. It's obviously in excess. And it formed carbon dioxide and water. And, of course, Q all by itself, since Q was not oxidized. Let's write down what we know about each of these. So we know we have 1 gram of compound Z, 1 gram of compound Z. We know nothing about the oxygen. We have 1.37 grams of carbon dioxide, 1.37 grams, and we have a small amount of water, 0.281. Okay. So we have those values. All right, so we're looking for the most probable formula. In other words, the empirical formula. We're looking for an empirical or a molecular formula, and let's just hope that they're both the same since nothing else was given to us. But we do have a lot of information. We're given information about how much of this we have, how much of this, and how much of that. Also, from a previous step, we also know that we have in our table that Z contains 59.3% of compound Q. Okay, that might play a part in this, so it's probably not a bad idea to write that. So 59.3% might be helpful. We'll see. All right, so we don't know if we'll use that or not. So let's do this. Since we don't have the formula for this, we don't know how much of this we have, we can find out exactly how much carbon we have and how much hydrogen. Because again, all the carbon and hydrogen comes from compound Z. So whatever is here is being produced there. This is our limiting reactant. This is all going to be used up. So we're going to take the carbon and the hydrogen and make carbon dioxide and water, and Q is going to be remaining with whatever else. Oxygen is in excess. So let's do this. Let's find out how many moles of carbon we have. So let's start off with what we know. We have 1.37 grams of our carbon dioxide. Now what's cool about this is we're actually doing a stoichiometry problem, but we don't have a balanced equation. What we have is a balanced chemical formula. So we can do stoichiometry on an individual formula just as easily as we can do on a balanced equation. And that's what we have to do right now. So to find out how much carbon, or how many moles of carbon, I'm going to find out, first of all, how many moles of carbon dioxide I have, and then do a mole ratio of how much carbon is in carbon dioxide. Actually, let's not use that color. So here's what I'm going to do. I'm going to convert the grams of carbon dioxide into moles of carbon dioxide. And carbon's a molar mass of 12, oxygen 16, 16 times 2 is 32, 32 plus 12 is 44 grams per mole. If I stop right there, that's how many moles of carbon dioxide I have. But I want to know how many moles of carbon I have. So I need to get rid of the moles of carbon dioxide. So, in 1 mole of carbon dioxide, how many moles of, or how many carbons are in 1 mole of carbon dioxide? Very good. I have 1 mole of carbon. Okay, so I can stop right there and get a value, whatever that is, and we'll do that here in a moment. And do the same thing with the hydrogen. Yeah, let's go. Okay, so I have 281 grams of water. What I'm going to do is I'm going to find out how many moles of water I have. So 1 mole of water, and that's 18.016. Let's just leave it at 18. And do our mole ratio. So in 1 mole of water, in 1 mole of water, how many moles of hydrogen do we have? Very good, 2. 2 moles of hydrogen. How do you know that? Because your subscript 2 says so. So in every water molecule, you have 2 hydrogen atoms. Okay, let's get some values for that first of all. So we get some interesting values. We get 0.0, let's say 311 moles, and 0.0311 moles. But the bad news is we can't just stop there and say, oh, okay, it's a 1 to 1 to 1. We have to realize that from our given information here, we have 59.3. And we know that Z has a molar mass of 64 grams per mole, so we can find out how many grams of that we have. Okay, so let's take our molar mass and let's find out how many moles we actually have, because we do have 1 gram. So this is kind of more of a problem solving technique here. So I have, let's see here, 1 gram of compound Z. And I know that in 1 mole of compound Z, there's 64 grams. Let's try something here. So 1 divided by 64 is equal to 0.0156 moles. And since we don't have Q, well, again, we're experimenting here. Let's just try something, see what happens here. If I say, okay, I have that many moles, and I don't know what Q exactly is, let's just pretend for a moment that these are the smallest ratios here. So let's say there's that. So in one molecule of Z, I will have, if I take that and divide it, 0.156, which is 2, and 0.156, which is also 2, tells me that I have 2 carbons and 2 hydrogens. Then I just have to find out what Q is. How can I do that? Let's see. If I take the mass of, now we predicted that Q may have a mass of 19, and again we can use that information. Let's do an experiment here, or just again, this is an interesting question that's been posed. If I had 2 moles and there's a 2 to 2, let's see, we've got 2 times 12, 2 times 1, so that's 24, that's 2, it's 26. Let's say that the molar mass is 64, okay? Follow me here. The molar mass of the compound is 64 grams per mole. If I subtract that from 26, what do I get? 64 minus 26 is 38. Ooh, I like that number. So if we have a 38 there, and we know that Q is 19 based on a previous step, then we can say that our empirical formula is C2H2Q2. So again, looking from up here, we say that it's 19. Here, let me lower that. So if we do, whoops, extend that a little bit. So we can say that, okay, we've got 19 divided by that gives us a 2, which really helps us to seal the deal on that. Get that back to normal size here. You're going to see some things on the AP exam. They're going to really cause you to dig deep, to do some problem solving.